Welcome to this video in which we solve for the tensions in each of the members of a truss by using the method of joints. The truss that we will solve is right here. It is designed so that it has 7 members and 5 joints. Each member is 1 meter long, which means that each of the angles here in the truss, every angle in the truss is 60 degrees. So our truss is made out of equilateral triangles. And let's suppose that we have a load at the very center of the truss of 1 kilonewton. So given the size of the members and the load, this would be like a small footbridge with a fairly chubby person standing on the middle or in the middle of the bridge. So what we want to do is find the tensions in each of the members. So what we'll do is begin by finding writing down a free body diagram of the whole truss, and we'll use this free body diagram of the whole truss to find the reaction forces, and then we'll go joint by joint through the truss to find the tension in each of the members of the truss. So let's begin by drawing the free body diagram. Okay, we have approximately drawn at least our truss that looks like this, made out of equilateral triangles. We have joints everywhere the members meet. And let's label the members. We'll start here as A, B, C, D, and E. And then we have the following reaction forces. On the left we have a pin joint, so basically our entire truss is free to rotate. This will give us an FAX. Oh, whoops. This will give us an FAY. Don't know what happened there. FAX. And then here we have an FEY. Okay. And at the center of the truss we have a 1 kilonewton load. And again, each of the members of the truss is 1 meter long. Okay, so again, let's look at the entire truss first to find these reaction forces. So if we look in the x direction, the only force in the x direction is FAX, and that's equal to 0. So there's basically nothing pushing the truss either to the right or the left. And next, let's look at the moment about A. Summation of the moments about A is equal to 0. Okay, we'll choose A because we have 2 forces going through A, and so if we choose A about which to compute the moment, then it makes life a little easier. We have only 2 forces we need to look at. So we have 1 kilonewton going downwards with a moment arm of 1 meter. So this is going clockwise, so we'll have minus 1 kilonewton times 1 meter plus FEY times 2 meters. Okay, this force here acts through a moment arm of length 2 meters. And this is equal to 0. And once we solve this for FEY, we get that FEY is equal to 500 newtons. Okay. So let's see, I guess we should be putting these down as we get them. FAX is 0 newtons. FEY is 500 newtons. And let's see, let's use then the sum of the forces in the y direction is equal to 0. I'll clear off some space to do this. Okay, so the summation of forces in the y direction is equal to 0. And we have FAY minus 1 kilonewton plus FEY is equal to 0. We know that FEY, this guy is minus 500 newtons. No, that should be 500 newtons. This is an arrow, not a negative sign. Okay, something was going to be terribly wrong there. We can solve this then for FAY to get FAY is equal to 500 newtons. Okay, so FAY is 500 newtons as well. Okay, so what this tells us is there is no horizontal force, and the load of the bridge of 1 kilonewton is equally distributed between the left and the right support. So, with that then, we can now just go through the truss joint by joint to figure out what the loads, the tension in each of the members are. And just as a reminder, as we go through this, we assume that at the joints that are put together by pins, there's no friction at any of the pins, so members are free to rotate any way they want to at joints, and that the members themselves are weightless. So you'll notice that we didn't take into account the weight of any members as we were looking at the bridge as a whole. In other words, we're assuming that their weight is negligible to the load placed on the bridge. Okay, so let's look then at pin A. Let's go to pin, okay, here we've got an empty screen, so let's put up pin A. Pin A, we had this force FAY. We have a force to the right, which is TAC, and a force up and to the right, which is TAB. And because I have equilateral triangles, all of my angles here are 60 degrees. Okay, so at these pins, we can only apply the sum of the forces in the x direction is 0 and the sum of the forces in the y direction is 0 because these are points, and so we can't look at moments about points. So I will have components of TAB. I'll have a horizontal component here. This is TAB cosine of 60 degrees. And I'll have a vertical component. This guy is TAB sine of 60 degrees. And I won't go through this in this sort of detail in the rest of these joints, but just to make sure it's clear, I've got an angle of 60 degrees here. I've got TAB on the hypotenuse, so this part here is given by TAB times the cosine of 60, and this component here is given by TAB times the sine of 60. Okay, and we'll be doing this a lot as we go through this free body diagram, or through each of the pins. So hopefully I'll make the assumption that you understand how we're doing this and why we're doing this. So let's sum in the x direction. And in the x direction we have TAB cosine 60 degrees plus TAC is equal to 0. And if we sum then in the y direction, we have TAB sine of 60 degrees plus FAY is equal to 0. And remember, we've already computed FAY, so we know this guy here is 500 newtons. So we can solve for TAB. So TAB will be equal to minus 500 newtons divided by the sine of 60 degrees, which, if we work that out, we get minus 577.4 newtons. Okay, so if you get a negative sign as a tension, don't worry. What it actually means is that the member you're looking at is in compression, not tension. So taking this number, plugging it in here, and solving for TAC, we find that TAC is going to be 577.4 newtons times cosine of 60 degrees, which, if you work out, cosine of 60 degrees is 1/2. So this will be 288.7 newtons. Okay, so we now have TAB and TAC. Let's go put these on our picture. Let's see, we have TAB and TAC. We have TAB, this is minus 577.4 newtons. And TAC is 288.7 newtons. Okay. Okay, so it looks like we're out of time for part 1. In part 2, we'll continue on with joint B.